Today, we shall discuss an object falling in air. Under this topic, we shall look at a body falling in air, and forces acting on it every step of the way during the fall. We shall use an example of a skydiver jumping out of a plane. Consider a skydiver jumping out of a plane that may be 3,000 meters above sea level. In the very beginning, when the skydiver just jumps out of the plane, the only force acting on him is his weight, that is, force of gravity. At this point, air resistance is very negligible, because his speed is too small. Because weight is the only force acting on the skydiver at this point, he accelerates at a rate of acceleration due to gravity. And why is that? Figure 3.1 shows forces acting on the skydiver immediately after jumping out of the plane. W is weight of the skydiver, and remains constant throughout the fall. R is the resultant, or net force, acting on the skydiver. Since weight is the only force acting on the skydiver, the net force equals to the weight of the skydiver. As figure 3.1 shows, no air resistance acts at this point. The magnitude of any force is represented by the size of the arrow. I wish to reiterate, no air resistance acts at this point. There is no arrow representing air resistance on figure 3.1. As the skydiver accelerates downwards, air resistance, which increases with increase in speed, starts to act in a significant way. In figure 3.1, we saw no air resistance acted. In figure 3.2, we see air resistance acts. At this point, there are two forces acting on the skydiver: weight and air resistance, as shown in figure 3.2. There are a few things I wish to emphasize here. Number 1. Air resistance acts vertically upwards, against downward motion of the skydiver. Additionally, air resistance increases with increase in speed. Number 2. Weight is acting vertically downwards, in the direction of motion of the skydiver. As mentioned earlier, weight remains constant throughout the fall. Number 3. By looking at the size of the arrows in figure 3.2, we see that weight is greater than air resistance at this point. Because weight W is greater than air resistance A, and that the two forces are acting directly opposite each other, the easiest way of calculating resultant force R is by taking the bigger force weight minus smaller force air resistance, as demonstrated in figure 3.2. The resultant force R should act in the same direction as weight. This is because weight is the bigger force. Number 4. From Newton's second law of motion, we know that acceleration acts in the direction of the resultant force. Hence, resultant force R, acting on the skydiver, and his acceleration, are both acting downwards. Weight is constant as it can be observed in figures 3.1, 3.2, and 3.3. We can see that weight is constant throughout. Now, because the skydiver is accelerating, or rather his speed is increasing as he falls, air resistance keeps increasing, as shown in figure 3.3. Air resistance 3.3. Then it was in figure 3.2. It was 0 in figure 3.1. Looking at all the three diagrams, we observe that air resistance has been increasing. It was 0 in figure 3.1 and started increasing as Skydiver's speed increased. We can see that air resistance is smaller in figure 3.2 than in figure 3.3. Because weight is constant, while air resistance keeps increasing, the net force R keeps decreasing as the Skydiver falls. Notice how the net force R keeps decreasing from figure 3.1 to figure 3.3. R was larger in figure 3.2 than it is in figure 3.3. It was greatest at the start of the fall, as shown in figure 3.1. Here, there was no air resistance. Remember, net force is the difference between weight and air resistance. From F equals to ma, and making acceleration a the subject of the formula, it follows that acceleration a equals to net force F divided by mass m. From this equation, with mass constant, as net force R decreases, acceleration a decreases as well. This means, as the Skydiver falls, his acceleration decreases. Eventually, the two forces, weight and air resistance, acting on Skydiver, become equal, as can be seen in figure 3.4. At this point, he now moves at constant velocity, called terminal velocity. If forces A and W are equal, the resultant force R will be 0. From the formula, acceleration equals to net force divided by mass. If net force is 0, the acceleration will definitely be 0. In a nutshell, as the Skydiver falls, weight remains constant. Air resistance keeps increasing due to increase in speed. The net force keeps decreasing, and so does acceleration. Eventually, air resistance becomes equal to weight. At this point, net force will be 0, and so is acceleration. When acceleration is 0, we say the Skydiver has reached terminal velocity. If nothing is done, the Skydiver continues downwards, with the terminal velocity reached, until he lands on the ground. However, this terminal velocity is very high, and not safe for his landing. The best option is for the Skydiver to open his parachute after reaching terminal velocity. Air resistance does not only depend on speed, but also on the surface area of the diver. Opening the parachute massively increases the surface area of the diver. Air resistance suddenly and significantly increases, exceeding the weight of the Skydiver, as shown in figure 3.5 on next slide. In figure 3.5, we see that air resistance is much greater than weight. This produces a larger net force, acting vertically upwards, significantly, and swiftly, slowing down the Skydiver. The reduction in speed of the Skydiver is massive, and takes place within an instant. This is because, when the parachute is opened, there is a sudden, and massive increase in air resistance, acting against the downward motion of the skydiver. As the skydiver slows down, air resistance, which also depends on speed, decreases. Air resistance in Figure 3.6 is lower than that in Figure 3.5. Notice that the net force R is also decreasing. I wish to emphasize that when the parachute is opened, the net force R acts like some sort of braking force. It acts as such because it is acting opposite to the direction of motion of the skydiver. Air resistance continues to decrease due to decrease in speed of the skydiver. Decrease in air resistance leads to decrease in the net force R. The trend continues until air resistance becomes equal to weight. The skydiver has now reached a second, but lower terminal velocity, safe for him to land on the ground. Note: when the parachute is opened, the net force R may be calculated by subtracting weight from air resistance. However, we ought to write a negative sign in front of our force value. The negative here means the force is acting in opposite direction to the motion of the skydiver.